So now let's talk about resistive wires. That is, wires that have a resistance that is appreciable as well as capacitance. In this case, we are usually talking about polysilicon wires or wires created in the diffusion layer. First, let's talk about the diffusion layer because it has a little bit of a specific curiosity about its capacitance. So unlike layers that are created above the substrate, diffusion is created within the substrate. And therefore, it does have a capacitance, but this capacitance is through the depletion region that it forms with the substrate, because usually this p-n junction between the diffusion layer and the substrate is reverse biased. The only exception to this is when diffusion is used to create a body or well contact, in which case we will not have a capacitance. So this is just a depletion capacitance that can be calculated. Of course, depletion capacitances are nonlinear and therefore we have to use average values. But depletion capacitance also increases with the area of the wire. So we still have to contend with the same trade-offs that we see with wires created at higher layers. Now, resistance also affects metal layers. It's important to stress this, especially in modern technologies which operate at high frequencies and suffer from the skin effect. Now, here's the problem with having wire resistance. You could say, well, okay, there's wire capacitance and we know how to calculate it, and there's wire resistance and we know how to calculate it. Let's just calculate each of these and then represent the wire as a resistance and a capacitance. And the question is, where do you put the resistance and where do you put the capacitance? Is the resistance at the beginning of the wire and the capacitance at its end? Is the capacitance at the beginning and the resistance at its end? Do you put part of the capacitance at the beginning and then the resistance in the middle and part at the end? And the answer is, of course, that resistance exists for the whole length of the wire. It is a distributed resistance, and the capacitance is also a distributed capacitance. So you have a distributed RC throughout the whole length of the wire. And so we have to find a way to represent wires that have this kind of distributed resistance and capacitance. Now, the problem with having a distributed RC network like this is that for the first time we have to deal with a network with multiple time constants. So in modules 3 through 6, we dealt with networks which had a single resistance and a single capacitance. We started to talk about having multiple capacitive nodes when we talked about charge sharing, but in the charge sharing model, we always ignored the resistance of transistors. Now, we have to deal with a case where we have multiple capacitances and multiple resistances. And in that case, we can calculate something called the Elmore time constant. And the Elmore time constant is a way to calculate a time constant in a network which has multiple capacitive nodes. And it only works when you have feed-forward path which have resistances and you have capacitances to ground. So you cannot have a feed-forward path that has a capacitance in it, because in that case you'd have coupling. And you cannot have loops. You only have to have a tree network with outgoing branches and feed forward. So let's, for example, calculate the Elmore time constant at this output node output for this input node in. So it's actually pretty easy. What you have to do is that time constant is going to be composed of multiple time constants, as many time constants as there are capacitances or capacitive nodes. So we go to the first capacitive node, and we find, first of all, of course, the time constant is going to contain the value of capacitance, and we multiply this by the resistance, which is in common between the path from the input to the node at hand and the input to the output. So we examine the path from the input to this node and from the input to the output node. What's the capacitance in common? And we find that the capacitance in common is R1. And so we multiply by R1. And then we go to the capacitive node C2, and then we're going to calculate C2 multiplied by the resistance, which is in common between the path from input to C2 and from input to output. So from input to C2, we see a resistance of R1 plus R2. In the path from input to output, we see a resistance R1 plus R3 plus R4. So obviously, the only thing that's in common is R1. So we are only going to multiply by R1 here. Even though on the way to C2 we observe R2, R2 is not on our path to the output node of interest, so we don't multiply by it. And then C3 is going to observe the resistance R1 plus R3, and this is also a resistance which is on the way to the output, so we observe here R1 plus R3. And C4 finally is going to be R1 plus R3 plus R4, and this will be the time constant for the node output. You can use this method to calculate the time constant for any node in this network. You can use it, for example, to calculate the time constant for this node, and you would consider that that would be your output node. So how do we use this and apply it to RC wires? I'm just going to take my wire and I'm going to divide it into n sections. Each section is going to have a resistance of Rw and a capacitance of Cw, meaning that the total wire capacitance is Cw times N, and that the total wire resistance is Rw times N. And so I haven't defined what N is yet, so N is an arbitrary number, and I just want to know what the time constant is from the input of the wire, which is this node, to the output of the wire, which is this node. And so I'm going to calculate the Elmore time constant, and tau is going to be, I'm going to look at this capacitance, the first capacitance, Cw, and I'm going to multiply by the resistance in common, which is Rw. And then this Cw, and I'm going to multiply by Rw plus Rw, so 2Rw. Then plus Cw into 3Rw, and obviously we have a pattern here. So this is going to keep going until we reach nRw times Cw. Now, obviously we can take Rw times Cw as a common term, and we end up with 1 plus 2 plus 3 all the way up to plus n inside the bracket. And we notice that inside the bracket we have an arithmetic sequence. So this is the sum of an arithmetic sequence. This sum of arithmetic sequence has an expression of n into n plus 1 over 2, and this is going to be multiplied by Rw times Cw. Now, if I imagine that n is really large, specifically, ideally, we want to divide it into an infinitely small number of sections, an infinite number of sections, each of which is infinitely small. So as n tends to infinity, this approximately becomes n squared over 2 times Rw times Cw. But n times Rw and Cw times n, each of these is equal to the wire resistance and the wire capacitance, respectively. And so this is going to be equal to R wire times C wire over 2. And so we find that the time constant of the wire is actually half the time constant that you would have expected if you consider the wire to be a lumped R and a lumped C, where you had an R followed by a C. So the time constant you would have observed here is Rw times Cw, R wire times C wire. Instead, we should observe half of that time constant. And that gives us the impression that we possibly could use this as a way to model resistive wires, but this is not true. This is only going to be valid if the resistive wire is being driven from a zero impedance node. This is not the case ever. So we always have a finite resistance driving the resistive wire, and the value of that finite resistance is R drive. If the resistive wire is being driven by a CMOS gate, this is going to be the Rn or Rp of the pull-up or pull-down network. But if you go back and look at row decoders and memories, for example, this could be the word line, and this could be the resistance of the final stage of the buffer in the row decoder that is driving the word line. But in any case, there's always a finite, though, preferably small resistance driving the wire. So if we calculate the time constant using the Elmore method here, we will not find that the time constant can be approximated as R wire times C wire over 2. So let's calculate it here. And here I'm assuming that I also have CD1, which is coming from the self-loading of an inverter. and CG2, which is coming from the gate loading of an inverter. So I'm assuming here that I have two inverters and I'm connecting them using a wire that has some kind of appreciable resistance. So let's start calculating the Elmore time constant, and the first capacitance, CD1, is going to observe a resistance R drive. The second capacitance, CW, is going to observe a resistance R drive plus RW. The third capacitance, CW, is going to observe a resistance R drive plus 2RW. And we're going to keep going on using this pattern until we end up with CW into R drive plus NRW for the last section of the wire. But we also have to calculate a partial time constant for the gate capacitance of the load inverters. So CG2 into R drive plus NRW. Now, this whole expression, of course, has some kind of pattern to it, so we can simplify it and look at what it means. So we have CD1 into R drive, and we have CG2, that's this gate capacitance, into R drive plus NRW. NRW is obviously R wire, so we can say plus R wire. Right, so you can see that for these first two terms, you have this capacitance being driven just by the driver, and the gate capacitance being driven by the driver and by the entire resistance of the entire wire. And then we're going to have terms that are related to the wire itself, to the capacitance of the wire itself, rather than to the load capacitances from the two inverters. And so we're going to have CW into R drive is going to be repeated n times, and so we have n CW into R drive. But obviously n times CW is equal to C wire, so this is gonna simplify into C wire. And then we're gonna end up with a term which contains CW into R wire plus 2R wire, and so on, all the way up to NR wire. So we're going to take, NR wire. So we're going to take R wire as a common factor outside, and we will end up with a summation, which is again an arithmetic series, which again simplifies into n plus 1 over 2, which in the extreme is going to be R wire into C wire over 2, and so we're going to end up with this term here. And so if we examine the total time constant, it does contain this C wire times R wire over 2, but it also includes other terms that have to do with the resistance and the capacitance of the wire that were introduced because of the presence of a finite drive resistance and the presence of load capacitances at the beginning and at the end of the resistive wire.